Guys, welcome back to my YouTube channel MK Tech. We discuss our remaining lecture and other application diode logic gates. Topic 4.3. Diodes together with resistors can be used to implement digital logic functions. Figure 4.5 shows two diode logic gates. To see how these circuits function, consider a positive logic system in which voltage values close to 0 volt correspond to logic 0 or low, and voltage values close to plus 5 voltage corresponds to logic 1 or high. The circuit in figure 4.5a has three inputs VA, VB and VC. It is easy to see that the diodes connected to plus 5 volt input will conduct, thus clamping the output Vy to value equal to plus 5 volt. Thus, this positive voltage at the output will keep the diodes whose inputs are low around 0 volt cut off. Thus, the output will be high if one or more of the inputs are high. The circuit therefore implements the logic or functions which in Boolean notation is expressed as y is equal to a plus b plus c. Similarly, the reader is encouraged to show that using the same logic system mentioned above, the circuit of a 4.5b implements the logic and function y is equal to a dot b dot c. This is logic gates, OR gate and AND gates. This is examples with help of solution. 4.2 Terminal characteristic of junction diodes. The most common implementation of the diodes utilize a PN junction. We have studied the physics of PN junction and derived its IV characteristic in chapter 3. The PN junction is used to implement the diode function. Should come as no surprise. The PN junction can conduct substantial current in the forward direction and almost no current in the reverse direction. In this section we study the current voltage characteristic of PN junction in the detail in order to prepare ourselves for diode circuit application. In figure 4.7 shows that the current voltage characteristic of silicon junction diode, the same characteristics is shown in figure 4.8 with some scales expanded, the others compresses to reveal details. Note that scale changes have resulted in the apparent discontinuity at the origin. The current voltage characteristic silicon junction, forward biased, reverse biased. The diode IV relationship with some scales expanded and other compressed in order to reveal detail. As indicated, the characteristic curve consists of three distinct regions. The forward bias region determined by V greater than 0, the reverse bias region determined by voltage smaller than 0, the breakdown region determined by voltage minus VZX. These three regions of operation are described in the following sections. 4.2.1 The forward bias region. The forward bias, or simply forward region of operation, is entered when the terminal voltage V is positive. In the forward region, the current voltage relationship is closely approximately by I is equal to Is e की power V over Vt minus 1. In this equation, Is is a constant for a given diode at a given temperature. A formula for Is in the terms of the diode's physical parameters and temperature was given in equation 3.41. The current Is is usually called the saturation current. For reason that will become apparent shortly, another name for Is and that we will occasionally use is the scale current. This name arises from the fact that Is is directly proportional to the cross-sectional area of the diode. Thus, doubling of the junction area resulting in diode with double the value of Is, and as the diode equation indicates, double the value of the current I for a given forward voltage V. For small signal diodes, which are small size diodes intended for low power applications, Is is on the order of 10 to power minus 15 ampere. The value of Is is however a very strong function of temperature. As a rule of thumb, Is doubles in value for every 5 degree rises in temperature. The voltage Vt in equation 4.1 is constant called thermal voltage and is given by Vt T over Q, where K is equal to Boltzmann constant 8.6 multiplied by 10 की power minus 5 E over K is equal to 1.38 multiplied by 10 की power minus 23 joules per Kelvin. The T is equal to absolute temperature in Kelvin is equal to 73 plus temperature in 0 degrees Celsius. Q, the magnitude of electronic charge is equal to 1.60 multiplied by 10 की power minus 19 coulomb. Substituting K is equal to 8.6 multiplied by 10 की power minus 5 E voltage per Kelvin into equation 4.2 gives V temperature is equal to 0.0862 T millivolts. Thus at room temperature 20 degrees Celsius the value of Vt is 25.3 millivolt. In rapid approximate circuit analysis we shall use Vt approximately 25 millivolt at room temperature. For appreciable current I in the forward direction, specifically for I greater than Is, can be approximated by a exponential relationship. I approximately Is E V over Vt. This relationship can be expressed alternatively in the logarithmic form. V is equal to Vi in I over Is, where I denotes the nature base E logarithm. Equation 4.1, the diode equation, is sometimes written to include a constant n in the exponential. I is equal to Is E V n k t minus 1, with n having a value between 1 and 2 depending on the material and physical structure of the diode. Using standard integrated circuit for fabrication process exhibition n is equal to 1 when operated under non-material condition. For simplicity we shall use n is equal to 1 throughout this book unless otherwise specified. A slightly higher ambient temperature 25 degrees Celsius or so is usually assumed for the electronic equipment operating inside a cabinet. At this temperature Vt is equal to approximately 25.8 millivolt. Nevertheless, for the sake of simplicity and to promote rapid circuit analysis, we shall use more arithmetically convention value of Vt approximately 25 millivolt throughout this book. The exponential relationship of current I to the voltage V holds over many decades of the current a span of as many as 7 decades. Factor of 10 to the power 7 can be found. This is quite a remarkable property of junction diodes. One that is also found in bipolar junction transistor and has been exploited in many interesting applications. Now guys, we stop our lecture and next remaining lecture in next video. So don't forget to subscribe my channel and